这个好像后面有。
对啊，全部是。这个话题好了，第一个动作非常简单，大家讲第三个动作，我觉得已经听出来了不少，让他就完成的。
这样能够算传输啊，
系统上非常小，它是小系统。
有一些super computer需要算这个东西，可是我们不知道怎么样传。
Okay, so good morning, everybody. So today I will introduce. I will say a few words about the electron-phonon interaction, how it is calculated in quantum espresso, and then also about phonon-phonon interaction. There will be another short presentation after this one. And should be relatively elementary, or at least I will not enter in many details. So the electron phonon matrix elements that one finds in formulas for electrical resistivity or phonon lifetime and electron-phonon interaction in parameters that enter in superconductivities are objects that, beside some frequency factor, describe the scattering of one electronic state from one electronic state to another electronic state induced by the fluctuating potential associated to a phonon. And so in our case, in the Kohn-Sham formulation, so psi k and psi k plus q are two Kohn-Sham orbital, and the scattering potential is the effective, the linear variation of the effective Kohn-Sham potential. That for a given specific q vector at a given and one specific mode, eigenmode, the q vector and eigenmode whose frequency is omega q nu. And since everything is linear, so we are in the linear regime, this delta v associated to an even q point and eigen vector then is simply a linear combination of the elemental variation of the Kohn-Sham potential when you displace one single atom S in a given cell in the Bravais lattice times the displacement vector times the phase factor associated to the q vector of the phonon, and then everything normalized the number of cells in your crystal. And these U are the eigenmode of the phonon of the dynamical matrix at Q. So this is the object that we want. Well, this is the basic object, and from this basic object one can calculate various things. For instance, the electronic part of the phonon line width is associated to some integral in the Brillouin zone of the all possible scattering processes induced by a given by this phonon, and obviously this scattering must connect let's say must connect an occupied state to an empty state, an occupied electronic state to an empty electronic state, and since the frequency of the phonon is very much smaller than the typical energy of the electron, the typical bandwidth of the electrons, then this actually this summation is restricted to states that go from just let's say below the Fermi energy to just above the Fermi energy, or let's say for very small and since the frequency is much smaller than the typical energies involved, then basically what we have to do is to integrate a double delta function. So we are connecting points from the surface, from one part of the Fermi surface to another part of the Fermi surface. Once you have this contribution, this gamma, running part of the phonon line width, then one can define more integrated electron-phonon interaction parameters like the lambda that enter into BCS theory of superconductivity, which is the integral of alpha square f of omega with the -1 moment of alpha square f of omega, which in turn can be then defined using this gamma q of nu. Again, integrated across the Brillouin zone and summed over all the possible eigenstates, and this will give you a function of omega when you integrate with this delta function. So, and this enter in various formulas. For instance, this is one formula, the Macmillan formula for the superconducting temperature, in which lambda is what we have defined in the previous slide, and mu star is some estimate of the electron-electron interaction, screened electron-electron interaction. So the basic quantity that we need is this one again, and the main point, the main difficulty is this double delta integration, because there are very few points that lie on the Fermi surface, and so if we make a sampling, you would need in principle an infinite sampling of the Brillouin zone in order to locate all the points on the Fermi surfaces, and here you have not only a single delta but a double delta. So even if you typically, as we always do, we replace sharp delta functions by Gaussians of some finite width, this is an integration which is very difficult to converge, and so one needs to perform calculation with a very dense set of k points. And so one needs to include in the band structure sampling a very dense grid of q points. On the other hand, this G matrix elements vary relatively smoothly in the Brillouin zone. So one strategy that is adopted is to, as I said, calculate on a very dense grid of k points the eigenvalues. So calculate the band structure of the system on a very dense grid of all points, and instead, which is not particularly difficult, so you can do you could do a circumsystem calculation with a reasonable number of points, and then sample in a non-circumsystem way, so keeping the same potential, the same circumsystem potential, and calculate the eigenstates on a very dense grid. And then calculate the phonons and this electron-phonon matrix element on a regular grid, but basically the same that one uses usually in order to calculate the phonon. That would be inaccurate to calculate this double delta integration, but it is accurate to have a good sampling of G and then interpolating the matrix element across the Brillouin zone whenever you need. Okay, so this is. So in practice, I don't have much to say, and I just want to let you understand the way the code and the exercise that you will do this afternoon. So what is the strategy that one adopt? As I said, one needs a very dense grid of Q points, of K points. So one runs a self-consistent calculation with a very dense grid such that this double delta is integrated accurately. An alternative would be to run first a self-consistent calculation with a normal set of Q points and then run a non-self-consistent calculation with a dense grid of Q points, of K points, sorry. But in the exercise we will just do, because we are going to do silicon, which anyway can converge quite fast. So we are going to do the self-consistent run with a very dense grid of Q points, of K points, sorry. I keep saying Q, but I mean K points and so on. And then one needs to calculate phonons and electron phonon matrix elements, and these are done by. And this, in order to calculate those, you do not need such a dense grid, and it will be a vast of time to use such a dense grid. And so one does again a self-consistent calculation with a dense but not extremely dense set of K points, and on the basis of this calculation then one do the full calculation for the vibrational properties, which are sampled on a regular grid of Q points, the way you have seen 2 days ago. And so then in such a way that then this sequence, these dynamical matrices can be transformed in real space to get real space interatomic force constant, and then you can Fourier interpolate throughout the Brillouin zone in an efficient way. And in the same way, matrix element of the electron phonon matrix element, this generalization of the electronic part of the lifetime line width, sorry, is computed. So this is an object in which instead of considering the diagram, to remember what, let me show. Okay. Here, this is the square of a matrix element that corresponds to one particular eigenmode. Instead, what this generalization is a generalization because S and alpha means that you are considering derivatives, matrix element, for electronic transition induced by a displacement of a single atom S in the Brillouin zone, in the Wigner cell, displaced in the direction alpha. So S and alpha describe an elementary displacement in the unit cell that then is repeated, get a e to the plus EQR phase when you move in neighboring cells. So S and alpha, S alpha is an elementary displacement, is not an eigenmode, and you need to calculate a square, and this square in this square you need to include not only the diagonal element, but also, I mean, all of diagonal elements. So you move, let's say, one atom S in direction alpha, and then you consider the coupling with the displacement of an atom S prime in direction beta. If you do like that, then the previous object, this quantity here, can be obtained simply by multiplying on the right and on the left by for any given eigenmode, you simply have to multiply by u alpha s and u beta s prime, and sum over alpha s and beta s prime. The reason why u is convenient to do that is because when you move across the Brillouin zone, the eigenmode may change and may get some phase, and you may have levels that are degenerate, and then when the symmetry is reduced, they become non-degenerate. So it's much, and this may induce, may in general make difficult to interpolate eigenmodes, because the eigenmodes may vary abruptly across the Brillouin zone, while this object is something that has the same symmetry properties as a dynamical matrix, has the same kind of indices, and varies smoothly in the Brillouin zone. So by calculating this object, one can Fourier interpolate this object to any q points in the Brillouin zone, and then for every point in the Brillouin zone where you are interested in, you similarly have Fourier interpolated the dynamical matrix, you diagonalize the dynamical matrix, then you get the local value of the eigenvectors, and then you make you calculate the expectation value of this of the interpolated matrix on each of the eigenvectors that you are interested in, and then you and you obtained in this way the gamma contribution for that specific mode. So this is basically what is done. So the code calculate these quantities and accumulate these intermediate quantities, and accumulate those things on the grid of k points and q points that are good for the interpolations. And when you calculate this integral, you need to perform a double delta integration. So here you need to put very many k points. So you use the k points of the point in the band structure that you have calculated accurately for many k points here. And whenever you need this matrix, this product of matrix elements, then you interpolate linearly between so this G you only have on the coarser grid, and so when you need them for the thinner grid, for the denser grid, then you linearly interpolate them in this denser grid. So you calculate this, and then with this, once you have calculated this quantity, then you can Fourier interpolate with respect to Q to any density you desire. So once you have done this integral accurately by linearly interpolating these two objects, then the integration over the Q space, over the reciprocal space with respect to the phonon momentum, then can be done very efficiently, because then there you can use the Fourier interpolation. Once you have done that, as I said, you can dynamical matrix phi and the coupling constant matrices that you have calculated on a regular reciprocal space in order to define interatomic force constant and real space electron phonon coupling matrices, and then from that you Fourier interpolate, and so you can calculate the integral of, for instance, alpha square f of omega with very dense grids. That's basically what I wanted to explain. I wanted to explain the way things are done. I mentioned that this double delta is replaced by Gaussian, so these two deltas are replaced by Gaussian, and there is no particular relationship between these things we are going to apply to metals. Particularly today we are going to see in the afternoon we are going to apply to aluminum. And so when we deal with metals, we use some smearing technique. Typically, we are not using pure Gaussian smearing, but we do some Marzari-Vanderbilt or McPherson-Paxton smearing. And instead, here, when we calculate this integral here, we just replace a simple Gaussians, and so there is no much relationship between this delta and the smearing that we are using here and the smearing that we have used in the central system calculation. And actually, these calculations are done for several values of the smearing. And in principle, what one should do is to study the convergence of the calculated quantities for increasing density of the electronic of the sampling of the electronic states for a range of smearing. So when the density, ideally what you would like to find is that the integral is accurate enough that from the smallest smearing that you are considering to some large smearing, the integral vary very smoothly. Okay? And then in such a way that you can, let's say, extrapolate to the limit of zero smearing, zero with the result. This may require very dense grids, and so this is something that one has to test. So what we will see in the afternoon is that we will use some dense grid, but not enormously dense, and so you will see that for the smallest smearing there will be some scattering in the results, which means that the sampling of the key points is not dense enough such that many pairs of k plus q and k enter in the product of the deltas. No? So when you do the integrals and you have only a small number of contribution for which this product is significantly different from zero, then this means that your sampling is not very good. Ideally, you would like to have a lot of k plus q and k plus qm and kn states for which this product give a contribution, because then you are averaging, and so the final result is some more or less stable number. This afternoon we will see that we will start from a rather small smearing, 0.005, so 5 millirietvert smearing, so rather small, and up to 50 millirietvert smearing, but the smallest value of the smearing and a rather dense grid, 16 by 16 by 16 points in the Brillouin zone of aluminum. So this grid, which is very dense for normal purposes, is not dense enough to integrate accurate the double delta at such a small smearing, while at larger smearing they level off and then you have a rather regular behavior. So this is something that one has to take care of, and so accurately check the conversion. Once this gamma of Q nu is calculated, then one can go back and calculate, for instance, this quantity, and then lambda, and for instance compare this with available results in the literature. And again, we will see, actually we will not compare with the results in the literature, but because we didn't actually downloaded some other previous calculation. But again, this is something that you can look as a function of the smearing. So this ingredient is computed with a given smearing and with a given set of k points, and so you can see how much this depends, how much sensitive it is, and one should convert the calculation until this quantity is stable. And then when you have this, then you can calculate lambda, and then you can, for instance, plug it in some, if you're interested to superconductivity, and you're interested to see how TC vary for different structural parameters, then you can use some of these formulas. So this is what I wanted to say about the electron-phonon interaction. So I didn't want to enter much into detail, and I would want to say similarly. I want to just